What's up, chemistry? We are going to look and start in with our unit on acids and bases. So let's go ahead and get started. Let's go to the next page here. And just a reminder, when we talk about charges, we got cations or cations, sometimes they're called, and anions. Cations are positive, anions are negative. Most metals tend to make a positive charge, most anions tend to take a negative charge. However, one that I want to kind of highlight here is hydrogen, because hydrogen usually has one proton and one electron. So if we were to look at the atom of a hydrogen, you'd have one proton in the middle, and then one electron just kind of floating around, shooting around at the near speed of light, bouncing around a whole lot. Well, if we make a hydrogen plus ion, if we take that electron away, all you're really dealing with is just one proton. So when we talk about acids and bases, you're going to see kind of hydrogen ions and protons being used interchangeably. So we're going to keep that in consideration when we're talking about acids and bases. So let's go ahead and do that. Well, for this class, we're going to use the definition of a base is that acids will tend to release hydrogen ions or protons or be proton donating when dissolved in water or some aqueous solution. So the concentration of those protons determines the strength of an acid. So over here you got vinegar. Vinegar is acetic acid. Maybe you can't really see that. I'll zoom out just a hair. So vinegar is acetic acid. It's not a very strong acid. It's pretty weak because it's pretty diluted. I mean, the concentration of the hydrogen ions in there isn't very much as compared to what would say maybe you would find on some citrusy fruit. So lemons or limes, for example. There are a couple other different examples for acids. One is stomach acid, and that is HCl. It's hydrochloric acid. This is the stomach acid that's in your stomach, your body produces to chew through food. Vitamin C is even a acid. I forget the name of it off the top of my head, but I'm sure it's ascorbic acid. I could be wrong on that. You can fact check me if you want. But in any case, what do all of these want to do? Well, when they're dissolved in a water or in a solution, they tend to donate protons. They tend to donate hydrogen ions. And when they do that, they kind of cause a chemical reaction called an acid-base reaction or an acidic reaction. And that's why if you were to pour a strong acid like on your skin, you might get slight irritation or it could eat through your skin. It really depends upon the concentration of those hydrogen ions. So, what can we do with acids and bases? We can name them. And so I'm going to hit pause on the video because I meant to throw a picture in here. Let me go get that picture. Okay, now I have the picture I was hoping to have for you. Let's look at how we name acids. They're pretty specific in nature, and they have some unique naming patterns. But let's go ahead and start with this. So all the acids that we're going to talk about in this class have to deal with some sort of hydrogen or proton donating acid. There are other types of acids, but these are the ones we're going to hit on in this class. So when an acid has only two elements in it, so like your stomach acid, for example, is HCl. What is the naming pattern we use when talking about two element or a very basic, or not basic, a very simple, I don't want to use the word basic, very simple type of acid? Well, here's what you do. We talk about the prefix, the hydrogen is the hydro for the hydrogen, chlor being our stem, and then ic acid. So back to like kind of where we would do like sodium chloride. So NaCl is sodium chloride. We chop off the end of chlorine and add IDE. Well, the stem is the chlor part, the part you didn't chop off when you are naming your compound. So notice how that stem is still there. So when you're naming acids, if they are two element acids or simple acids, just look at the stem of that second element and it should be pretty good. All right. If they have three elements, usually one of those extra elements is going to be an oxygen or involving an oxygen. You're going to need your polyatomic list. because these have usually some sort of polyatomic ions with them, and so we have to use our polyatomic list to name these acids. If that polyatomic ion has an ATE ending, like nitrate, for example, so we have nitrate, we look at the stem of nitrate, and we use that. We just add the ic ending, so it's instead of nitrate acid, it's nitric acid, and that's it. If we have nitrite, for example, we still use that stem. Notice nitrate and nitrite have the same stems, so we do have to make sure we name them differently when we're talking about acids. So instead of nitric acid, it's nitrous acid, and there you go. It takes a little bit of practice on these, kind of getting through it. So let's kind of do some practice right now. All right, we're going to draw, and we're going to name each of these and draw what their dissociation is, where they placed in water. Where does that hydrogen ion come from? So hydrogen fluoride, I'm just going to write those out. So we got hydrogen fluoride. But we chop off that ending. We don't want that ending anymore. We're going to chop that off. And instead of hydrogen fluoride, this hydrogen becomes hydrofluoric acid. There's the H. There's the F plus the ic acid. Pretty straightforward. HCl is going to kind of get the same treatment. We give it hydrogen. We give it chlorine or chloride. We chop off our endings, and this just becomes hydrochloric acid. Not too bad. There's our H for the hydro, chlor for the chlorine, ic to make it an acid, and there you go. And then last one, but surely not least, is this complicated mess right here. If I were to take out one of the hydrogens, what polyatomic would I be left with here? And that would be acetate. So if we look on our list and find acetate, we notice that this is a hydrogen plus acetate. Or you could say hydrogen acetate, but we really don't since it's an acid. So what we're going to say then is we're going to chop off we're going to look at what kind of ending we have. We have an ATE ending. So if we go back to our little kind of note right here, ATE endings, we just chop off the ending, we leave the stem, and we add ic. So acetate, we remove. And so what do we have? We have, got a little crazy with that handwriting there. Let's try it again. Acetic acid. Notice there's no hydro. And that's because this is a polyatomic ion acid. So since we have multiple things, notice that when we have three elements, we don't put the hydro in front. Okay? What would these do if we dissolve them in water? Because in order to make it an acid, in order to be proton donating, in order to be ripping and tearing through stuff, it has to be proton donating or hydrogen ion donating. So, HF, for example, when we put that in water, it breaks into hydrogen ions and fluorine ions. And there's your acid right there. Same thing with hydrochloric acid, HCl. When you put it in water, there's your hydrogen, there's your chlorine. Pretty easy. And what about sodium acetate, or sorry, not sodium, acetic acid? We have the same thing. You're gonna dissolve it in water, so it's gonna be CH3COOH. CH3COOH Well, it turns into OO. Give it a minus charge. And then we have H plus. And so that's why these turn into acids when you put them in water. When they dissolve, when you put them in water, they break apart into their hydrogen ions plus their counterparts. There could be some specific language for that, but we're not going to talk about it in this class, at least not this week. Okay? Let's flip the coin a little bit. Let's talk about bases. Now, bases sound safe. They actually can be just as dangerous or just as concerning as acids are. So in the same way that acids can eat through your skin, so can bases. Now, a lot of cleaning agents are actually basic in nature. You know, your bleach, your toilet bowl cleaner, your things like that. Usually, your blood is as well. If you're just sitting at home, kind of on the couch, at rest, your blood tends to be slightly basic. If you just got done working out, your blood might be slightly acidic, or even maybe neutral if it wasn't that hard of a workout. So what do we do with bases? Well, a base is the opposite of an acid. So rather than being want to donate hydrogen ions, they tend to want to pick them up. So they pick them up by ripping and tearing through other things. So if an acid and base are put together, they can kind of think of it, they neutralize each other. They cancel each other out. So when you look at a base, we talk about the concentration of OH or hydroxide ions. So the concentration of hydroxide ions determines the strength of the base. The stronger the concentration, the stronger the base. Now let's look at naming some of these. And there are no special naming patterns. Yay, no special naming. It's just like you would do all of your other polyatomics. So NaOH would just be sodium. Oh, handwriting got away from me. Hydroxide. You guys should be a champ at naming this stuff by now. Lithium hydroxide. Not too bad. Or sodium carbonate. Sodium carbonate. So what do these do when you throw them in water? Well, when it comes to sodium hydroxide, when dissolved in water, it makes the Na plus and your hydroxide ion both be dispersed in the water. And this part is where your base comes from. That is the part that is dealing with the hydrogen ions and wanting to accept them. You know, because if a hydrogen ion came, prancing in, it's going to be attracted to the OH, not the Na. Because those both have a plus charge, they're actually going to repel. So, lithium hydroxide, it's going to be super similar to sodium hydroxide. We got LiOH. That's going to be lithium plus and OH with a minus charge. Not too bad. Okay, now you might be asking about, what about NaHCO3? What's kind of going on here? And if we look at our structure for sodium carbonate, it's NaC double bonded O H. I feel like I'm missing an oxygen here. I sure am. Oh, I'm going to erase this real quick. I'm going to continue the recording here. I actually made a mistake. A little boo-boo. This isn't sodium carbonate. This is sodium bicarbonate. Goofball. That's what I get for not having my polyatomic list with me. So when it comes to the dissociation here, what's going to happen is that we got NaHCO3. You're going to have your Na plus ions with your HCO3 polyatomic ion. And this is going to act like a base as well, because in here you do have an OH group. However, it's considered a very weak base. So it's not very strong. So if we got sodium bicarbonate or baking soda, if you were to wash your hands with it, it wouldn't be that bad. If anything, it would be used kind of used as a cleaning agent some ways in your house. Anyways, let's keep moving forward, and let's talk about the pH scale. So we talked about acids, we talked about bases. What about the scale in between? So when we look at acids and bases, we give it a scale of 1 to 14, with 7 being neutral, nothing else is going on, and 1 being anything less than 7 is acidic, anything more than 7 is considered basic. So you can kind of see now how they're opposite ends of the spectrum. Well, let's talk about a couple things that might fall on the scale. So your blood, like I said, is slightly basic, and that is 7.4, a pH of 7.4. Water is pure 7. So in between, not one way or the other. So that's why if your body if you do a lot of working out, it actually can become slightly acidic and go below 7. It can, usually not for very long, but when you use your muscles and you're working out, you actually produce lactic acid, and so your muscles tend to get a little acidic. What's some other things that have some low pH on them or very acidic? Your urine tends to be acidic. Tomato juices, some people have a very sensitivity when eating tomatoes. That's because of the acidic nature in them. And then your stomach. Your stomach does a really cool job. It produces hydrochloric acid, so it produces a very strong acid to eat away your food. But your stomach lining around your stomach or inside your stomach, prevents that acid from eating your stomach away. So your body produces something to chew it, but also protects you at the same time. If you have like heartburn, indigestion, or some digestion issues, usually it could come from that stomach lining is either damaged or your stomach's not working properly, and that acid is getting somewhere it really shouldn't be. But a lot of household cleaners, including hand soap and bleach or toilet bowl cleaner, tend to be very basic in nature. They just tend to work better than acids when it comes to cleaning. So we've talked about the pH scale. You go from 1 to 14, 1 to 7 being neutral, 7 to 14 kind of being basic. Not too bad. So let's wrap this up with putting a couple of different formulas in our pocket. And you're going to kind of need these when it comes into it. So if we're to look at the scale of pH, where it being from 1 to 14, we can look at the concentration of hydrogen ions or the concentration of hydroxide ions when it comes to the pH scale. For reasons we don't quite get into for the math right now, but pH plus pOH is always going to be equal to 14. So if we look at the pH of something, so if something has a pH of 12, that means the pOH is 2. Or the concentration of hydroxide ions is, a lot less than the concentration of hydrogen or protons in the solution. They're there, but in a very, very small amount. So when we look at pH and pOH, all those numbers have to be equal up to 14. So if we wanted to find, for example, the concentration of hydroxide ions in an acid, not in a base, but in an acid, we'd have to use kind of potentially all of these formulas in one breath. Notice a couple things which might go wrong is that pH is on a logarithmic scale. So it's a negative logarithmic scale too, so make sure you put that negative in there when you're doing it. But what we're going to do is we're going to do some practice problems and just see if we got it. So what is the pH of water? Well, that's easy. pH water is 7. Boom, it's always going to be 7. You can't really change it. What is the pH of an acid with a concentration of 0.05 m molar of hydrogen ions? So we're just going to use that pH formula. So pH equals negative log concentration of H plus ions. So pH equals negative log, where's the log button? There we go. Negative log 0.05. 1.301 That's it. We just maybe round that to 1.3. So let's say just approximately 1.3. Not too bad. What is the concentration with a pH of 3? Well, this one does take a little bit more of some finagling. So let's see if we can get that down. If we come to a logarithmic function and we need to rewrite the log, well, let's just do a basic function. So we've got y equals log base 10. So usually when you say log, you mean base 10 log x. So if we were to rewrite this, we could rewrite this as 10 to the power of y equals x. And let's use a little bit of a... Well, I started here at 10 to the power of y equals x. We're going to have to rewrite our formula for the next one. This is kind of like a refresher, so let's do that. What is the concentration of an acid with a pH of 3? So we're going to use the pH formula again. So pH equals negative log base 10 to the concentration of hydroxide ions. Looks all right. So let's just continue on. So pH is going to be, excuse me. Sorry about that. I had to sneeze. Or at least I thought I was going to sneeze. But we're going to rewrite this with in consideration of this. We have to find this concentration of H, but we have to get rid of the log. So I'm going to plug in the numbers we have. We got 3 equals negative log base 10, because if you write just log, it's assumed to be base 10, concentration of H. Well, we're going to take this negative, get to the other side, so we get negative 3 equals log base 10, concentration of H. Not bad. Now let's rewrite it. Might scooch down just a little bit. Well, that's going to be 10 to the power of negative 3 equals concentration of hydrogen ions or protons. So we just plug that in our calculator. 10 to the power of negative 3, which is 0.001. That's it. Okay. All right. For the sake of time, I'm going to cut the video here. You're welcome to try these other questions. If you have questions about the questions, absolutely feel free to reach out. You guys are awesome. Stay awesome. And I will see you in class.